All right, so like we said, we've been going through it. Remember, there are how many different ways to calculate delta H? There are 5 different ways. We've covered 2. The 2 ways we have done the stoichiometry and we have done calorimetry. We started with Hess's law the other day, and I think I may have to go back one slide real quick. Okay, yeah, so Hess's law, remember there was something specific about Hess's law. What is the delta H value for an element in its standard state? 0. All right, so when we saw this, we had this. First of all, what is the name of this compound? Benzene, very good. And what type of reaction? Combustion. And so we wrote Hess's law, which is delta H of the reaction is the sum of the products minus the sum of the reactants. Again, what are these purple numbers? The coefficients. This is important. Now, I told you there was one thing that was left out of the Hess's law calculation that's in a reaction. What was left out? Why was that left out? It's in its standard state, so it would have been 0. Okay? And then the final question I asked you, read the question up here. How much heat is released, what, per mole? Well, in this particular reaction, how many moles of benzene reacted? 2 moles. So when you got your calculation, what did you have to do to your final answer? Divide it by 2. Hypothetically, what if it had been 12? You divide it by 12, whatever the coefficient is on that particular compound. What if it would have said how many moles of energy is absorbed with per mole of water? What would you have done? It would divide by 6. But what would the sign of delta H been? Positive. Very good. Okay. All right. Did we do this problem? All right. So let's do this one real quick. So we've got 3 Al, so 3 aluminums plus. Let me pick on somebody. Mary. What is the name? Mary Fabrini. What is the name of that formula? Ammonium what? Anybody? Perchlorate. Okay, or hyper or per, either one. So ammonium perchlorate, solid, plus aluminum oxide yields aluminum chloride, plus nitrogen monoxide, and then water. Okay, so we've got all these things going on, and then again, this is a cheated version down, but they give you all the substances. So here's the first thing I want to do. I want you guys, and again, if you have space down beside it, or you have space out to the left, if you're on the iPad, if you want to add a new page, it's in there. Thank you. I want you to write Hess's law using the formulas. Not numbers, using the formulas. And I kind of see some blank stares. So we're going to write delta H naught of the reaction is equal to the sum of the delta H of AlCl3 plus, and then continue on. Because we're going to do the sum. Well, really what this would be is this is the brackets. You really could eliminate the sigma if you wanted to. You don't have to. Yeah, because you're saying the sum of the sums. Sum, seven. Did you say you're going to start doing what? Probably not a good idea. All right. right, so here should be your products. Now, here's the deal with the products. There are two things in two different colors. Why are those things in different colors? Nope. Nope. They have coefficients. They have coefficients. Is it NO? My apologies. All right, so they have coefficients on them. And again, coefficients matter. Every year, students understand how to put all these numbers together and add them and subtract them and all that cool stuff. But every year, they always leave off the coefficients, and that's what makes that's what makes this hard, is because people don't pay attention to the details. Now, whenever you wrote the reactants, and I promise I'll come right back to this, but there's something about the reactants that's different. So look at your two reactants and then look at the chart. What's weird? One of them is missing. Which one? Aluminum is missing. Now, that's the problem. It's not just because it's a solid, because look, ammonium perchlorate is also a solid. So what do you need to really say? In its standard state. And so that's why aluminum is going to be left off. Now, there's also something special about ammonium perchlorate, and what is it? It has a coefficient of 3. So NH4, that's wrong. ClO4. Okay? All right. And so this is what we're going to have to do. And now, once you have all this written, then what do you do? Plug the numbers in. Okay? So this is where it's going to... Now, this is the part where I am going to need your help. So we've got delta H of the reaction. What was the value of AlCl3? Negative 704. Any decimals? Nope. Okay. What about Al2O3? 1600 and what? 6. Okay. And then plus the value of NO? Positive 90. All right, okay. All right, and then what about the value of water? Negative 242. All right, and the top ones, they have coefficients. Yeah, and I didn't feel like changing pen colors the entire time down here. And so, again, right here we've got a coefficient, and right here we've got a coefficient. And finally, we're going to subtract it from, what's the value of ammonium perchlorate? I promise I'll move in just a second. What's ammonium perchlorate? It's right there. Negative 200. Negative 295. Okay? So, now you can tell it's not hard, but is it easy to mess up? Yeah, it really is. You know where numbers go. You've been plugging numbers in your entire life in these different formulas. But when you've got this many numbers to plug in, and you also have the coefficients on top of it, that can really cause an issue of making sure that the right numbers go into the right places. Because let's pretend that you have all the products on the right side, but what happens if you invert the numbers in front of the wrong coefficient? You mess it up, right? So do you see how whenever we did electrochem, remember when I gave you that whole entire sheet that you could see how it was easy to put the wrong number down even though that you knew exactly what to do? Same concept. It's easy, but it's easy to mess up as well. You just got to make sure that everything goes into the right spot, and once it goes in the right spot, you got to make sure your calculations are correct. Yes, sir. Okay. That goes back to the rule that any element in its elemental standard state has a delta H of 0. So it doesn't matter, so you leave it out of the calculation. Now, in terms of order of operations, what would you do first? You would multiply the coefficients first. So would it probably be a really good idea to have a graphing calculator to do this one? If you have one of the basic scientific ones, it would take you forever to do this. Forever. Okay. So whatever you need to do to make this work, does anybody have the answer? Really? Did you make that up? Okay. All right, so negative what? 4,400. Okay, we'll do that. Now, there is one thing I want to do. What units are all these in? Here's a question. Right here, What are the units? There isn't any. So I'm telling you now, please, 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 pay attention to the tables, because the next few chapters we're going to get in, these tables are going to be very crucial to you paying attention to the numbers. Okay, I promise I'll answer the questions in a second. Now, here's the deal. What did we actually just calculate? Delta H. What is a very special thing about delta H? Kilojoule per mole of a reaction. Okay, make sure you get the kilojoule. Yes, sir. What's wrong? Is the answer wrong? Did you subtract? Well, yeah, technically you would add it, plus and minus. So my question is, you agree it's not difficult, the organizing it, the plugging numbers in, but making sure the right numbers go in the right location and the calculation is correct. Say that again. He got negative 2,600. Yes, sir. No. Yep. All you did was take, Devin, these numbers, plug them in, multiply by the coefficients, and subtract it from that number. Yep, they're already there. Now, I'm going to be honest, a lot of reactions they give you already balanced. A lot of them are. Because it's in a standard state. Okay? All right. Now, here's another way that they could ask you this exact same question. Now, here's the deal. Pay attention to this, because you're fixing to see a question in just a minute that was actually on the AP exam a few years ago, where they did this exact same type of question. So I'm going to help you do this one, and then I'm going to give you a chance to do it on your own. So sometimes, guys, y'all stay with me. Nick, okay. Sometimes all values are not found on the table of thermodynamic data. For most substances, it is impossible to go into a lab and directly synthesize a compound from its free elements. The heat of formation for the substance must be found by working backwards from its heat of combustion. Now, what does that mean? My first question is, what is this compound? Glucose. Where do you have glucose? Photosynthesis, AP, and all that other stuff, right? So do you agree that that glucose goes through combustion? Yes. This process in biology was called This is cellular respiration, okay? How do you know it's cellular respiration and not photosynthesis? These two, it reacts with oxygen, right? What do plants use? So this is really the key indicator. You find out what side the oxygen's on. That tells you which one it is, okay? So, but here's the problem. We know that we give off energy, right? Specifically, every time you have a mole of glucose, it will release that amount of energy, 2,800 kilojoules. For how many moles of glucose? 1 mole of glucose. So here's the question. Read here in white. Find the delta HF of glucose from the following information. So what are they actually asking you for? They're asking you for a part of the entire reaction. Guys, this is just like finding X in an algebra formula. This is all you're doing. They give you the total, and they want to know what the middle part is. Does that make sense? Said. All right, so let's do this. My first question is there any of these reactants or products that will leave out of the Hess's law formula? Why are we going to leave oxygen out? It's in its standard state. Now, my other question is, down here in the table, glucose isn't listed on the table. Why? That's what we're trying to find. I don't want you to assume that it's 0. That's why I asked that question. Oxygen's not on there, but why is it not on there? It's standard state. Very good. So, all right, so let's plug this in. All right, so we've got Hess's law. So we've got the delta H of the reaction is equal to the delta H of carbon dioxide. Hang on, what was the... You can do it however makes it work for you. My brain, I want to start from what I know is right and then rearrange. I like to start from the initial state. Yes. That's the total delta. That's right there. This is going to be 2,800. Yes, that's where 2,800 is going to be plugged in. Yep. Now, my first question, what was the coefficient on carbon dioxide? All right, so 6 CO2. What about water? 6 H2O minus, and then glucose, right? All right, so we're trying to find C6H12O6. This is what we're trying to find. Yes, and that's what we're fixing to talk about. So this entire reaction, so the combustion of glucose gives off how much energy? 2,800 kilojoules. Now let me ask you something. When you plug this in, this is the delta H of the reaction. So when I come back over here and I plug in 2,800 kilojoules per mole, what side of that reaction was that number on? So what does that tell you about this number? Very good. If you do not put that in right there, how wrong will your answer be? Very, very wrong. That's where they're going to get you. They're not going to tell you delta H is equal to a negative or positive number. They may show it to you in the reaction form. And here's what, and I promise I'll come back to this. Here's what happens. Some students will see this sign right here, and what will they assume? That it's positive, but you got to remember that it's on which side of the reaction. The product side, which means it's what type of reaction? Exothermic, and exothermic has what type of delta H values? Negative. That's very important that you catch that. All right. Now, I am going to need your help on this next part because I can't see the numbers. All right. So, I've got 6 times what's carbon dioxide? Negative 392.5. Negative, my bad. Negative 393.5. I'm used to it. Plus, what is water? Negative 285.8. And what am I going to be subtracting? Now, obviously, do you have to plug in X? Can you plug in glucose? Can you do whatever you want to do? Sure. It's just a variable. This is basic algebra with chemical formulas. Very good. Exactly right. Okay. So again, it's not hard. It's making sure things are in the right place. Because if it's in the wrong place, it's really going to mess you up. And the second thing that I probably would assume that would be most missed is that right there. And you got to catch that. I can't teach you that other than you just recognizing that that number has to be negative because it's a reactant. Now, from this part, if you were in algebra, how awesome would it be to have that on a test? You would be pumped, right? Okay, that's basic algebra that you should be able to do. What is that? What, 8th grade math, maybe? I'd say 7th grade math. Now, there is one part of this that I need you guys to understand. And I promise I'll come back to this slide, but I want you to notice this. And I'm going to clear this page so you can read it. Please read the words in white one more time. The delta H what? F. There's something important here. So this is what we need to read now in blue. Page, stay with me real quick. I need you to hear this. This is why this is important. This right here says delta H of F. Well, we need to understand what that means. Delta H of F is heat of formation. So the entire reaction is delta H of what? The reaction. But we're not solving for delta H of the reaction. We're solving for delta H naught F. Okay? So is there a difference? On the exam, if it says calculate delta HF, do you write it exactly as it has it written? Yes. Do not deviate from what they have written. It's obvious they're trying to help you. Let them guide you through to what they want to know. So then whenever you find this answer, you can just plug it in. So what will the answer be? You're making stuff up. Okay. All right. Positive or negative? Positive 12. All right, so let's just go with 6. So it is negative? Okay. So maybe this is harder than it sounds. Multiply 3 times this. Multiply 6 times this. Add them together. Then what do? You don't, there shouldn't be any other than dividing by -1. You subtract the brackets minus -2800. Then divide by -1. I go ahead and tell you that that's going to be a positive number. The brackets is greater than -2800. Should be, so it'll flip it to a positive number. Yep, and then you divide by negative. Say it again? Okay. Listen, Sarah, listen. Everything in the brackets. Listen. Everything inside of the brackets. So you've already multiplied, added. Okay, that's negative. Take that number, and you're going to add it. Excuse me. You're going to subtract it. Subtract, but plus a positive. What was this number in brackets? What? All right, so here's the deal. I need to add this to this side because I got to get it to the other side. Oh, the answer. Yeah, that is the answer. The units, yes. We're just talking straight numbers, straight math. I mean, this is the basic algebra part, and y'all are freaking out. All right, so we're good there. So that's the answer to that one. So here's the one I want you to solve, guys. This was from 2014. This was question number 6, part C. See if you can answer this particular question. So I think most of you have kind of gotten this. Yes. But here, I want to give you one inkling. Guys, here's the problem, Mary. Okay, y'all tell me. The question is important because the question is, determine whether the combustion of propene releases, and here's the whole thing, more or less or the same amount. Now, let me give you an example. Regardless of what the answer is, what's the first sentence that you need to write? Blank releases, propene releases blank than vinyl chloride. Does that make sense? That's the first sentence you need to write. And whatever you do calculation-wise, you fill in the answer. Does that make sense? So propene blank, energy than vinyl chloride. Justify your answer with a calculation. So the only thing that you're going to be using, the only equation you're going to be calculating, do you agree, is this one right here? Yes, no, maybe. So in the data chart they gave you, how many of those numbers will you not need to utilize? 2 of them. Well, definitely, yes, 3. That one, and which other one? That one. So you don't need any of those 3. Why do you think they put those numbers there? To throw you off, to confuse you, to make you utilize them. Now, could you possibly plug 0 in? Yes, but there's no need to. The other 2, the HCl and the vinyl chloride, you will not use because of the calculations, all right? So here is their exact answer. This is exactly what the AP exam had. So they had, and again, I don't like the numbers. I actually like writing the formula so you know where it came from. So where did Where did these two numbers come from? Hang on one second. No, what was this number? This was CO2, right? This was H2O, and this was C3H6. Okay, and then the numbers are in front of the coefficients, and this is what they got. Now, here's the deal. When you did that, what's a little bit different from what we've done prior to this? How many did any of y'all divide that by 2? Very good. So here's the deal. The problem is, reread the question. What did the question say? It says with 2 moles. Well, look at both of your reactants. This is 2 moles, and this is also 2 moles. So you can have them comparatively. So this is negative 3,800. So the combustion of 2 moles of propene releases more energy. So that's all you had to say. I agree with you. I don't like this. I agree with you. I agree with you. It should not be. But I think the reason they can get away with it is because the question stated 2 moles of propene. I agree with you. But they got away with it because of the question. Mary? Yes. Very good. Now here's what do you think most students did when they got this 3858? If they divided it by 2, that gave them a number less than 2,300. So that's going to be your problem. You have to really pay attention to what they're going to give you. What if this top one, what if this vinyl chloride was, what if it was a 1? What would you have to then do? You would either have to double the 2,300 or half your answer. You got to get them in the same mole-to-mole ratio. Say it again. Yes. Yep. Okay. All right. So you got 1 point earned for the calculation of enthalpy of combustion of propene and 1 point earned for the comparison that consistent with the values. Hypothetically, let's say that you did put right here, what if you divided that by 2, but your comparison statement was correct? Could you still earn one of the points? You could still earn 1 point. If you divided this and got less, and right here you said propene releases less energy, you still could have earned this second point based off BOA, right? Does that make sense? Okay, so even if you fudge those numbers, you can still earn partial credit because of going with the right way. All right. Now, so we're moving on to the 4th method. Remember, there are 5 different ways to calculate delta H. This is going to begin talking about the 4th method, and it's called Hess's summation laws. So here's my question. What is going on from the green circle to the green circle? What reaction is occurring? Combustion. What is specifically combusting? So you remember whenever we drew the thermodynamic graphs, what was that top of the hill called? That's the hill. What's the top of the hill called? Okay, right there. You're right. Hold that statement. That's the next question. This is called the transition state, which Peyton, these things in the transitioner state are called what? Intermediates. And this is going to be very crucial to us throughout the next few years, or next few weeks. So if we have A going to B, remember, is there stuff going on inside that arrow that you can't see? Yes, and that's where this next part comes in. Notice what's happening right here. Do you agree that 2 different reactions are occurring? Yes. So what happens is this methane must be broken down into part of the reactants. So this would be your intermediate state. And so what can happen is these things can be broken down into individual steps. So Hess's law states that if a reaction carried out in what? That blue, the last part in blue? Series of steps, the delta H for the overall reaction is equal to the sum of the individual steps. Now, this is probably the most hated part of thermochemistry, is figuring out how to make these steps work for your advantage. Okay? Because the delta H is a state function. What does a state function mean? Doesn't matter how you got there. Do you agree that this methane is going to get to those products regardless of how it got there? Could it have 12 steps in here? But guess what? It got there, and it's going to release a certain amount of energy. But we can divide these reactions into multiple steps. The total enthalpy, again, what is enthalpy? Energy, which is H. Change depends on only the initial state of the reactants and the final state of the products. This purple words under this picture, we're going to be hearing a lot. The reaction mechanism. And that is basically how things are set up, how it's designed. So in circuits, do you agree you can design a specific circuit that has many different ways to get there? But in the end, does it have a certain amount of voltage that goes all the way through? Yep. Okay, so that's exactly what's going to be happening. So this is a reaction mechanism. It's that I and D. No. It's the types of matter. It does depend on the amount of matter, and it doesn't depend on the amount of matter. Yes, thank you. It's an extensive thing. Delta H's or state functions are intensive things. Non-state functions are extensive things. Okay. So prime example, extensive is like work. So if the more like in heat, so the more heat you have, the more work you can do, right? Well, the less heat you have, the less work you can do. So does it matter how much you have of those things, the amount of results you get? But the state functions, it does not matter how much you do, just like the fan and the heater. We have a certain battery. It's got a certain amount of power, and no matter how it does it, it's going to use all that power. I agree with you. I don't really know why they have that particular statement. Yeah. All right, so here's the deal. So this is going to be the reaction. My first question is, you just kind of saw this. What was the prefix for 3? The prefix for 3. We just saw it. Pro. So what is this? This is propane. Okay? So what is propane going through? Combustion. This just told you that propane goes through how many steps in order to combust? 3 steps. So let's look at the first one. So notice right here. This is the important statement right here. This is reactants. What's the first thing the reactants go through? What stage? Step number 1 is they go through decomposition. So what does propane, when it reacts with oxygen, turn into? Graphite, hydrogen gas, and oxygen gas. That's the first stage. And if you notice right here, actually it's a typo. Add this for me, please. This is a typo. Plus 5O2 gas. Write that in for me. That's a small typo. So again, this is the first step. Now let me ask you something. What is the delta H of that first step? Positive 103 kilojoules. So what type of delta H would that be, endo or exo? So do you agree that it has to absorb some energy to make these new steps? Okay? Now, this is again occurring in a step. This is occurring in steps, so it's called this yellow word. This is a very important word. What's that yellow word? Mechanism. All right? So that's step 1. Now, notice what happens in step 2. What happens in step 2? The formation of 3 carbon dioxides. Now, formation. What is your delta H there? Negative. Okay, so notice what happens. You had to put some energy in. It created something new. And then what happened when you form carbon dioxide? It released a little bit of energy. Okay, so you have, well, a lot. So you have the 3 graphites, the 4 hydrogens, and the 5 oxygens come together to make what? 3 carbon dioxides, 4 hydrogens, and 2 oxygens. So that's what's going to happen. And then what was the final step? The formation of water. So notice what happens. You've got your 3 carbon dioxides and your 4 hydrogens and 2 oxygens come together to make how many waters? 4 waters. And so that's how the entire thing goes. So if you notice from the beginning to end, we started with these reactants and ended with what? Those products. But how many steps did it take to get there? It took 3 steps. I got it. Yes, that's fine. Okay. And that's the thing, is it happens so fast that you don't realize it's even happening. But here's the crazy part. Each one of these steps has its own thermodynamic graph with its own specific activation energy. But whenever we draw it as one entire entity. So if we go back and we look at this, you just told me that it happened in 3 steps, right? So really, we could have step 1, and then we could have step 2, and then it can go on like this. But obviously, the 2 hills would need both amounts. It's the total activation energy. Yes, it's the sum of all the activation energies required. And so, but it doesn't matter, because if you do delta H, it's here to here. Doesn't matter how we got there, we got there. And that's why mechanisms are kind of tricky.